Ajibade, please confirm.
Normally it was scheduled.
30
The entire
minutes.
program was supposed to be for an hour, but we spent some time. Maybe we can have like 45 minutes if that's fine with you.
All right, so
Yeah.
let's see where we go from there.
Thank you.
All right, please confirm you can see my screen.
Yes, sir.
Yes, we can.
So, good afternoon, everyone. So today, as being said earlier, we're talking having a discussion around the fundamentals of Prosper software for production optimization. So we'll be having a live walkthrough of this software. So my name is Olayemi Samuel Ogundele, a graduate trainee at Cypher Christian Limited. So let's begin right now. So just have a quick before then. I want to get to know you better. So if you are joining in as YP, just drop YP. If you are joining in as students, just drop ST. I want to so that we'll know where we go from here. So please just let's try to make it engaging. Okay, I'm saying ST. I'm saying YP. Okay, let's keep it coming. I'll be keeping my eye on the chat box. Please other let's I like to have interactive sessions, so I don't like talking just all by myself. So I want to be sure that you are with me. Okay, STYP. Okay. So from what we have now, we have a mix of it. So no problem. Go from here. So yes. Our icebreaker session. Can you still using the chat box? Can you name any software specifically designed for the oil and gas industry that you know? Do you know anyone, any software that you've heard that is specifically designed for the oil and gas space? Petre, wow, okay. Petre, Team Russia, okay. Okay, keep it coming. Eclipse, okay. All right, Eclipse. All right, so I'm expecting to see Prosper as well, but it's fine. Eclipse are very common out there. Petre are very common out there. So, and one of it now is Prosper. Even if you don't know before now, so you are getting to know today. So the next question will be, have you used any of this software before? Either Eclipse, that Prosper, Petre, as the case may be. Okay, someone mentioned Prosper. No, no, oh, oh, all right. That's good then. Then, do you think you can access and use this software? Do you think it's accessible? Is it something you are willing to you can get? Is it something you can easily lay your hand and get out there? Or do you think it's even possible for you to get it? Very difficult. Yeah, exactly. So that will possible but not easy. Yeah, yeah, I love that. IPM package. Okay, yeah, I think that's it. That very complex. Okay, IPM package is responding to any software. If you've come across any software before, so complex, very difficult, possible but not easy. Yes, very, very. That will lead me to a very maybe short story that made me come across a Prosper. So I think it was in my 300 level, where then I've already bent that I want to learn at least one industrial software before I leave the school. But the question is, how do I get it? It's very, very complex. It's very, very difficult. one of my colleagues is on this call. He can actually attest to how difficult it is for us then. Then I now went in straight to one of my lecturers and asking that, how do we get this? Then he told me straight up, like the truth, the blatant truth that these softwares are not easily come by. So if you have to pay for it, then the question now arises that do I even have the money to pay for this? Lo and behold, I don't have. So then out of my curiosity, relentless trying to get this because I'm very, very determined that I'm going to learn one software before leaving the school. And possibly if I learn that software, it's going to be what my project is all going to be around what I'll use for my project. Lo and behold, after a lot of search and try and there, so I got my hand on one, which is the IPM package as um, someone put in the chat box there. So the IPM package, which comprises of this Prosper that we're going to use today, it comprises of PVT, P, Ember, Gap, and the likes. So moving forward, yes, you can get it, it's possible, but it's very, very complex because the licenses are not cheap. That's just the basic, and it is not like every other industry that you can just easily get those software. So, but now, yes, through IPM package, you can at least can be like me, learn one of this software, and I'm very, very sure it's going to be helpful to you. So moving forward, so now our topic says something around production optimization, but how do we even um discuss production optimization without even understanding what the production system is all about? So, and our production system to some people, it's just the surface facilities. When we talk about separator, we talk about compressors out there, but production system, it's actually bigger than that. So, and production system begins right from the reservoir. Then, before you get to the wellbore, then before you begin to see the surface facilities, all those gas stations and whichever station you've come across. So the reservoir is where energy resides. Yes, this is where the whole energy that drives the production actually reside. So a reservoir engineer must design a system that is sufficient and capable of driving these resources out from the reservoir. Then the productivity depends on the reservoir pressure, yeah, and the reserve. So before we want to think of drive mechanism like water drive, so the pressure itself like has to be very, very very, very top notch, like designed in such a way. That system must be designed in such a way that the reservoir pressure is sufficient enough. And one of the things that drive this reservoir pressure is when we have a strong aquifer beneath our oil system. So it's going to be a very, very supportive in terms of pressure, initial pressure that brings out the resources from the reservoir into the wellbore. Then this wellbore begins with trying to create a hole into identify feed or identify area for potential oil and gas. So, and this process of boring this hole is called drilling. Then after drilling, that's just you creating the hole. Then another thing you have to do then before that, you have to do your casing. So some people term casing and cementation as part of drilling, while some see it as a transition between drilling and work completion, whichever case you see it. So it's very, very important that there must be casing and cementation. And I believe that most of us have the basic knowledge of this and why we need to do that. So I won't be going deep into that. Then where completion now comes into play, where we have insert a lot of accessory in which will help us bring this oil into the surface, and this comprises of tubing, comprises of safety valves, comprises of mandrels, paca, and a lot of the like that. So oil is then produced through this tubing. Then you must isolate the wellbore, create an isolation between the wellbore and the and the fluid using packer, wellbore and the tubing string using packer, so that your fluid only flows through your tubing to the surface. So the next thing is the surface facilities for onshore. The surface facility begins with well head, which houses our tubing head housing, casing head housing, and the likes. Then the next thing that follows it is a Christmas tree, which contains several valves for regulating our production from the well bore. Then that's for onshore. Then when it comes to an offshore, this wellhead and Edgeman's tree can still be considered as being at the subsurface because it rests on the bottom of your on the surface that's beneath water that is on your sea floor. Then the riser will now bring it to the surface. Then after that, we have separators where initial separation comes into play, which can be two-stage, that is separating just liquid and gas. Then it can be three-stage, liquid, gas, and water. So depending on what you have, then compressor helps you to maintain the pressure of your gas when you want to flow it through the flow line. Then the pumps help you apply pressure to push your fluid. So we have a lot of all these surface facilities, but again, I just want us to have a basic understanding of this production system because we cannot understand production optimization without even understanding what the production system is all about. Then the total production system, this is the image of what we're talking about, begins with let me see if I can use my, excuse me, no, pointer. All right, this is a reservoir, then being perforated so that the fluid in the reservoir can enters into our wellbore. Then this is a tubing string as mentioned. So packer will be somewhere here so that all this fluid coming in will be confined into this space and be able to be pushed within this tubing because we want to produce through tubing. Then this safety valve as a means of emergency. During drilling, we have a blowout preventer. So during completion and production, we begin this safety measure through subsurface safety valve. It can be tubing retrievable, it can be of any type. So then you can see this is still below, this is the sea level, then this is beneath, this is the bed. So then it comes out, our Christmas tree is there, it comes out, then our riser takes it to the surface, separating it to oil and gas and exporting it to taking it to maybe somewhere downstream or midstream. So the next thing first to talk about is factors influencing production decline. Yes, apart from the normal routine optimization, so something must have propelled you wanting to do the optimization, which is as a result of production decline. So the production decline can either be in the reservoir, it occurs in the reservoir, it occurs at the wellbore. Also, it can occur at the surface, and also fluid property can also contribute to the production declines. Then on the reservoir pressure depletion, naturally, the pressure in the reservoir is expected to push oil to the surface, but as you produce along the line, so there's going to be pressure depletion there. So which means a reservoir will not be producing as the way it's supposed to be produced. So which through optimization, maybe introducing of artificial lift system or water flooding to support the aquifer, can help us to maintain the pressure there. Then water or gas cooling, that is when you start producing, when water begins to enter into your oil system, then that's another way your production can get declined. Then formation damage, when there is not enough permeability around the well bore, maybe caused by maybe fine particles entering, blocking the well bore, blocking the pores, that is perforated pores that bring fluid into the well bore. So poor reservoir connectivity can also be another thing. Worse asphalting or skid deposition can also occur near the where your well is being connected into the well bore. So those through those perforation. Then another place is that through the well bore tubing or perforation blockage. Then corrosion or mechanical damage, like mechanical damage can be in form of scales and all this in your well bore. Then inadequate artificial lift performance. If you don't have artificial lift performance plan in place, then that can be another way your production can decline. Improper choke settings. Yes, you need to regulate your choke properly for you to have a proper production. Then gas locks and pump. At the surface, separator inefficiency, if your separator is not doing what it's supposed to do, there's definitely going to be decline in production. Then pipeline restriction or leak, when there's leakages in your pipeline, obviously your production decline, or when there's a restriction, maybe deposition of was, deposition of skills can also lead to that, and it can even cause a more serious issue such as a back pressure, that is that pressure reducing your drawdown pressure below beneath the well. That is when your drawdown pressure is very low, then you'll not be able to not be able to not be sufficient to push those oil upward. So that restriction in the pipeline can also at wellhead and anywhere can cause all those back pressure that reduces your pressure drawdown, because you actually needed a large pressure drawdown for you to be able to lift that well correctly. Then compressor or pump malfunction can also be another problem. High back pressure from export line. Then fluid properties, increased viscosity. Maybe your temperature, the temperature drops can actually lead to your fluid being viscous and not being mobile enough. Then higher water cut. When you have a influx of water in your production, when you have water breakthrough, then gas liberation, that is when your bubble point, your reservoir pressure is now below bubble points, there will be liberation of gas, and that can actually, because you're most interested at that point, you're most interested in oil, then you'll be having a mixture of oil and gas in excess. So yeah, that's another problem. So moving forward, we've discussed about production decline. Then we need to talk more now on the we've seen the problem, then how do we solve this problem? That brings us to production optimization techniques. So reservoir optimization comes first here, then reservoir pressure maintenance, like I said, you introduce you introduce things, maybe water flooding to support your aquifer, so that you maintain the pressure in the reservoir, so that the pressure in the reservoir will be sufficient enough to push your resources to the surface. Then enhance oil recovery, maybe thermal flooding, CO2 injection can also help in solving this problem and improving your reservoir performance. Then well bore optimization, artificial lift system. In most of the completion, there is always a provision for maybe a mandrel, to be precise, where you can actually have that injection of gas and the likes. So apart from gas lift, you can also use ESP, that's electric submersible pumps. And another thing you can do, I think most people will have come across a soccer rod pump. So those are the artificial lift system that we can use in optimizing production. Inflow enhancements, ensure that there's enough enhancements things you use for the inflow. Then flow assurance, we ensure that your pipeline are free of scales, walls, and the rest. Then compression and pump optimization. You ensure that your pump is working optimally and your compressor that's supposed to be compressor is in a good working condition. This help you to maintain your surface facility and driving production optimization. Then operational optimization, digital oil feed. I believe one or two people or more than that here, but I've heard about digital twin. This allows you to look at what is happening on your field directly, and this can help you in a predictive maintenance, which also will enhance your production because you don't have to always be there. You can actually predict what is going to happen with the through digital feed. You monitor everything. Then economic optimization. This is very, very important. You ensure that whatever you're producing is of economic value. So you don't want to go and drill a well or producing from a well, or the money you are using to produce from a well is even more expensive than the money you are getting from it. So you need to balance that economic aspect of it also. Then another thing here is the fluid property optimization, emission control. You can reduce the emission through using chemical treatments and the likes. So that's we actually need that production optimization techniques, and this is one of the things Prosper will help you to do. All these things here, Prosper will help you to do that even before you begin or during your production. Before you begin, you can actually predict using Prosper software. So that is the reason we're having trying to build this what is it called? We are trying to build this foundation so that you understand that this Prosper software is very, very, very important and very, very powerful in your production, in your production system, as the case may be. So now, before we go into that introduction to Prosper software, because it's also good, we have that introduction here also. I believe you are following. If you're following, just type Y. If you have any question, you can raise your hand. Maybe we'll take a pause. Okay, I'm seeing Y. So okay, we are following. We are following. All right. So let me continue. So you can start penning down your questions. So we'll take it later. So introduction to Prosper software. Prosper, is a well-designed optimization software, which is part of integrated petroleum modeling toolkits by petroleum experts. Like I mentioned earlier, it comprises not only Prosper, as you can see here, this is IPM Prosper. So there's IPM Ember, there's IPM Gap, which does other things. There's IPM Resolver, there's IPM which other one there? Resolver PVTP. So a lot of those applications does a lot of things. So, but now we're focusing on the Prosper, and this Prosper optimize the operation of steps to optimize the operation of the existing well, and also predict the effects of future change in reservoir and production parameters. So it helps you to understand what is happening in your well at that point in time. You can do that simulation and understand what is going on in your well. Then another thing that will help you to do is to help you to determine or have an idea of future changes that may occur in your reservoir and your production parameters. So it's a very, very powerful tool for now, for the moment, and to help you forecast what is going to happen in the future as regarding to your well and your reservoir. So moving forward, like I said, it has a lot of capabilities. And one of the capabilities, it can model various type of fluid. Maybe it is oil that you want to model, it is water, it is dry gas, wet gas, uh, it does a lot a fluid characterization comprehensively. So another thing is flexible well configuration. It simulates tubing flow or annular flow, or you can even do the combination of two. Perhaps you want to, is a new well, you want to the best approach for you to use. Yeah, Prosper will give you that leverage. Then another thing is which for production optimization is very, very important, is a diverse artificial lift design. Yeah, Prosper software houses ESP simulation and gas lifts, then also can also be jet pump system. Then detailed sound control management. It can help you to build a gravel park well, pre-park screen. So I just have to bring this for because there are a lot of things Prosper can help you to do, which we cannot just finish talking about at this point in time. So I just brought out these four, and our case study will be around one or two of these. So now it's time to get our hand dirty for real. So we'll now do the live walkthrough. So and now we're having a very simple case study. So now, like I said, one of those modeling capability. So we're going to be modeling a gravel park well and carrying out system sensitivity analysis. So this Prosper can even help you to carry out node analysis, sensitivity analysis. That is when you carry out sensitivity analysis, you're trying to compare which is the best for me. And node analysis too. That is, you're trying to at any point there's a pressure drop, that's a node, and so you want to. It can help you determine all those kind of a thing. So, but now focus on let's focus on modeling a graph and carrying out a sensitivity analysis, and if time permits, we can look at artificial lift too. Why this case study? I think it boils down to a personal experience I had that it propel this. That's one of the reasons for this software. My network is unstable. Please confirm you can still hear me.
Yes, we can hear you.
All right, so based on to personal experience, there was this I think during my internship. So what happened was I saw a complete I saw somewhere I saw a complete well walkover, like removing of tubing. I was like, what happened? Has this well be producing for 16 years, 10, 20, 20 years, 30 years that warrants this full walkover? They said no. I began asking more questions that how long has the well been producing? They said 3 years. I said, what? So if you are doing complete walkover, like removing the string, trying to perforate, trying to run all those accessories again, which costs millions of dollars, and within that 3 years, the cost of drilling the well in the first place has not been covered, because drilling wells run into millions of dollars. So, which I believe in those short period of time, they've not even really recovered. So I now begin to ask those questions. What could have happened? They said they've started producing sand. Which average lifespan, I don't know if I'm having that correctly in my head now, around maybe 16 years or so for before any kind of serious workover can be done. Though normal what is it called? Few maintenance can be carried out within that period. Well, so it is well. So now that's now brought me to since they want to do gravel park, they said they did not do gravel park. So this is a good software for you. This is a good landing for you to let me, even if I'm going to use case O, yes, they only case the whole, and I'm not even sure they case it properly. So they only do casing or then what they are planning to do is they're going to case, they are going to perforate, case the hole again. Then another thing is they are now going to introduce gravel pack. So this Prosper software can actually save you all those stress by modeling your well before you even start. So that is why I'm bringing this case study up. So now let's go into the software. So we'll stop share. Okay. So are you seeing my screen change to Prosper software? Please
Yeah,
confirm what
we are
is
seeing
on
the
my
prosper
screen.
screen now.
Oh, okay. All right. So, all right. So this is Prosper software. This is the interface that comprises of the option summary, PVT data, IPR data, equipment data analysis summary. And this is version 11.5. There are other builds now that are very, very sophisticated than this, but this is what is accessible out there. And as at the time I was looking for software, this is what I can lay my hand on, being the free one. So let's begin. This is save button. We use all these buttons when we get there. So let's begin with option summary. So like I said, we are going to build a graphical model. So the fluid, oil, and water will remain. Yeah, method is black oil. Separator, single stage separator will do emotional. Hydrate, disable warning, all those things. Let's leave it the way it is. Well type, yeah, is producing. Yeah, we are producing through tubing. Artificial lift. Let's focus on the gravel park well now. We'll come back to artificial lift if the need arise. Then the predict should be pressure, temperature, offshore, then rough estimation full. Then well completion now, case O, agreed. Then sound control. This is what we change here to gravel pack. So we can do gravel pack, we can do pre-pack, wire wrap screen, slotted liner type of sound control, but let's do gravel pack control, sound control. So the inflow type is single branch, then gas coding. We assume no gas coding. Then the user information, you can input the name of the company, feed location, web platform, and the likes. So having done this system summary, we click on done. Then the next thing we want to input is our PVT data. Then I prepare some data, though not a representative data of any well, but for the case of this demonstration, I'll be using these figures, which I'll be entering shortly. Okay, so let our solution GR be 1820. And then oil, that's definitely oil because solution GR below 5,000 is oil. Then oil gravity, let's say very light, 43.6 or 3.6. Then gas gravity 0.81. Then water salinity assumed to be 23,000. So more percent hydrogen sulfide impurities. I don't have any information on that. Then our correlation, yeah, for now we select Glasso for the bubble points for the solution gas correlation, oil formation volume factor. Then for oil viscosity, we select Bellator, though we have Bex, Petrovsky, and the likes. Then for the PBR, RS, and Bill, we have Glasso standing, Lazata, and the likes. But I will stay with Glasso and Bill et al. So another thing that is very necessary is okay, our laboratory data, because this matching of data is especially in PVT, matching of data is very, very important because we have this all these Glasso, they carried out those experiments in very different locations. So it's important to do that correlation with what we have here. At least then we'll be able to select the best that fit into our environment. Let's assume this data is collected from nature data and Glasso and Bilito carry out the experiments somewhere far away from this country. So is that correlation, my matching of data that will help to determine, okay, which of those correlation are very close to what is obtainable here. So that's why that point is important. Then let me quickly enter some value here. So let's say the first pressure is 4650. The solution GR is 645.3. Then formation volume factor is 1.312. Then oil density, okay, oil viscosity now. Oil viscosity. Okay. Oil viscosity. Do I have oil viscosity? Okay, let me just, since I'm assuming, so let me just do this. Let me do what I have here, 0.7550. And the next one is 3915, 645.3, 1.317, 0.7498. Let's do for life. 5.3300 versus 3.5, 1.321, 0.7595. Let me just enter one more to save time. 500, 108.6, 1.1, 0.8301. Ideally, we have more than these pressure points from our differential liberation experiments. However, let's just stick with this one for the purpose of this demonstration. So let's say our bubble point is 3915. So the temperature is 176.7. So having done that, then you come to done, click done. Then the next thing is you want to carry out that calculation. You click regression. So in the newer version, you see something like match data. So now I want to match all. Should take. So I'm matching for bubble point, gas oil ratio, oil formation volume factor, and oil viscosity. So it's taking a couple of time to do that. All right, in 26 seconds, calculated for all the use cases. So now the standard deviation is very, very important here. Standard deviation below around 0 is very, very good for our correlation. So which means Glasso is very, very good here. The Glasso ratio, I think there's an issue there, which we're not going to look at that much. Then oil formation volume factor, this is still a good number. Then oil viscosity, which means Glasso is good. Then let's try to check another one. If we have, let's check Almaron. So 0.2, 0.030, and there's an issue with this GR. So let's check one more. Lasata. So zero, the value are not that close to 0. So let's stay with the Glasso. So now we are done. Do we plot? Okay, nothing else here. So done. So you can see this blinking this screen that our PVT is matched and we are good to go with Blasso and build it up. So we are done with that. So the next thing we want to enter is our IPR data. IPR is basically our inflow performance relationship, which means the deliverability of our well the deliverability of the reservoir into the well bore. So basically. So here we have a lot of reservoir model, but if you could remember, there's a place we choose inflow type as single branch. So in that case, we'll be using DASI. So we can use productivity index entry as one of the reservoir model. can use composite, we can use Vogel, a lot of them there, but let's use Dazi. Then mechanical and geometric skin, let's select Caracas and Tariq. So there are a lot of mathematics behind this, and there are a lot of reasons behind it that we're not going to go deep into. So why all this? So for the deviation and partial penetration skin, we're going to choose Cinco Martin. Then before going forward, we need to enter the reservoir pressure. Let me see if I have it here. Okay, our reservoir pressure is 4241 psi. Then the temperature of the reservoir, 189. So the other temperature I entered the other time is for PVT and is lab, but this is what is happening on the feed. So let's assume we have 0 water cut. And we are good there. So we go to input data, where we input our reservoir model, which is DASI that we choose. So what is our reservoir permeability? Let's assume it's 689 millidasy. Then our reservoir thickness is around 40.3 feet. Then our drainage area is 1910. Then for radial flow, the test shape factor is around 31.6. That's for radial flow. Then our Weber radius, let's assume is 5. So that's our reservoir model. The next thing we want to enter is our mechanical geometric skin. So we have our reservoir permeability there already. Then shot density should be around 8 shots per foot. The perforation diameter is 0.45. Then perforation length, let's assume 9.2 inches. Perforation efficiency, let's assume we have a very perfect perforation. So sticking with 1. And the damage zone thickness, that should be roughly, let me just put 500. No. This thickness. Excuse me, damage zone thickness, let's say 10 inches. Then the reservoir damage zone permeability around 500. Like I said, all these figures are just assumed for the case of this demonstration. So it does not represent a true figures. So cross zone thickness 0.2 inches. Short cross zone permeability, let's say 200 millidasy. Then short facing around 120 degree. Then let's assume our vertical permeability to be 100 millidasy. So we are done with that. Then let's input for skin Cinco-Martin bronze correlation. So the deviation is going to be around 13 degree penetration. Yes, let's assume that's a very perfect penetration because it's in fraction, so we're supposed to have a total of 1. So let's assume we have that 1. Then after imputing that, then our sound control, which is very, very important value we need here. So I don't know if you can see the right hand side of it that we have typical values. So gravel type, we have Ottawa sand, carbolite, and isopac. So the mesh size 50/70, that is 50 micrometer can enter a 70 mesh size or those kind of thing. Then the lab permeability. So I will be going with this 50/70 Ottawa sand. Let me say we have 30,000 millidasy. So this again, this is standard from the laboratory. So that's why I'm fetching directly from there. So short density gravel pack length, let's say is about 6 inches. Perforation interval. So let's say we perforate around 30 feet out of our 40 something feet of our reservoir. And then we can calculate so method. Let's leave it as single phase. Let's say single phase, then yeah, the beta turbulence will be calculated. So the next thing we want to do is we've entered all those information, and then let's calculate. So now, just by pressing that calculate, we have our absolute open flow, which is the maximum happens to be the maximum production rate at the least pressure, which is and the pressure here is around 1.1. So that's our absolute open flow. And then formation productivity index is around 40.7 skin. Yeah, the skin is an issue here because is signaling that it's damaged because the skin is above zero. So which can be as a result of this gravel park and causing damage around that wellbore. So in short, we have our IPR plot, that is inflow performance relationship. We can determine our absolute open flow, which is the maximum flow rate. I don't know if you are seeing this side of it. Yeah, rate, STB per day. So maximum flow rate at minimum pressure. That's our absolute open flow. As yes, for the reservoir. Then we are done with the IPR, then done. So the next thing we want to input is our equipment data. So this has to do with these two important concepts in petroleum production, IPR and VLP. VLP, IPR, like I said earlier, deliverability of fluid into the wellbore. Then delivering the fluid into the wellbore or our oil into the wellbore is not the end of our production. So we have to look at another concept, which is VLP, vertical lift performance, which is deliverability of that fluid beneath that wellbore into the surface. So that's a simple term. I don't want to speak big grammar. So just as easy as that, deliverability of the fluid into the surface, VLP, and into the wellbore, IPR. So you should be able to remember that. So now we need to configure our equipment data. So let's click all. And then I don't have information for surface equipment. I'm on checking that. Then let's edit and put the required figures there. So for deviation survey, we have starting from the surface, nothing is deviating from the surface. Then the measured depth, I have 11,474 as my MD. Then the true vertical depth is around 11,347. I believe that we actually know the difference between true vertical depth and measured depth, so I shouldn't do more or talk about that at all for the case of this. Then on downhole equipment, so first is starting from your Christmas tree, which is at the surface, so the feet is 0. Then you can begin to have other things in there. Just click on type. Okay, let's say we are starting with okay. Let me say we are starting with subsurface safety valves, which is somewhere around okay. Let's say the tubing inside diameter, let's say around 3.5. I think that should work. Then let's say the next thing we're having is our tubing. Our tubing measure depth. Okay, let's say is at 11,347. So definitely we are not casing the whole stuff. We are not going to insert tubing to the end of the well. So our tubing is not expected to sit like where the measure depth is. So now there's this allowance that we are supposed to have a flow there. So the next thing I want to input here is the tubing diameter. Let's say it's the same size with the inner diameter is the same size, 3.5 inch, and we have the rate multiplier is 1. It's just, let's assume we have 1. Casing inside roughness, all these that are not editable, so you ignore it. Then the next thing is let's say our casing. Let's say it's somewhere 11. Let's say let's assume we case to bottom 474. Let's say 464. So the casing inner diameter is assumed to be 5.5 inch, and we have one. So you can have multiple of them, to being another casing, another any form of restriction. This restriction can be no go locator in your tubing, it can be XN, it can be X, all those things cause restriction there. So you need to factor that out when you have that in your completion design. So, but now let's just stay with this. So done. Now there are geothermal gradient. I think I have some values for that. So formation depth is at 0. Then this at the surface, the temperature is 60 degree. Then below, that's for the measure depth. Then the temperature of the well is 189. Then our British thermal unit, let's say it's 8.6416 as I have here. So done. So it automatically compute our average heat capacity. Capacity of oil is 0.53 BTU, gas is 0.5, and water is 1. So automatically computes that for us. Then let's look at the summary of what we have. So this is the summary of what we have. Then we can visualize what we have here by drawing, go to draw down hole. So you can see this is our SSSV, subsurface safety valve, 15-inch. Then this is how it looks like. Then our tubing 3.50, then casing to the measure depth. So this is our downhole equipment, and at the surface is a demonstration of your Christmas tree, a schematic of your Christmas tree. So having done that, finish, then done, then done. So we have our equipment data. Then the next thing, we've input all the necessary data. So the next thing we want to do is we want to do node analysis. Like I said, at every point where there's pressure drop, it's called a node. So, and those things can reduce our productivity. So we need to, Prosper will allow you to do all those combination of those nodes, okay, evaluate it and see what happened. So let's go to calculation. We want to see our IPR and VLP. So let's select 3 variables. So let's say assume our top node pressure to be 500. So water cut is 0. Our total GOR carried forward is 1820. Then surface equipment correlation BEX and Brio, petroleum expert, solution node, bottom node, rate automatic liner, just leave that the way it is. Then you continue. Okay. Let's continue first. Then let's calculate. So we're going to, clicking this calculate, we're going to have a liquid rate, oil rate, VLP pressure, IP pressure, change in pressure of total skin, all those values in no time. So we have all this here as our table. So our liquid rate is around 6,377 STB per day. Gas rate is 11 million standard cubic feet. Oil rate is 6,377. So there's no water there. So because our water rate is 0. So it makes sense that oil rate and liquid rate is the same. Solution node pressure, wellhead temperature. This is the summary of the results. So we have our results here in 20 places. So that's on that. Then let's visualize it by clicking plot. Let's see system plot. Okay. So let's change the variables to oil rate and click done. So these are the 20 points. This is the IPR curve, inflow performance relationship curve. Then this is a VLP curve. So the most important thing here is this point. They call it what is it called now? Operating point. That is the point where our IPR and VLP is in equilibrium. This signifies the point at which any amount of liquid here signifies the liquid that will be present at the surface, because it's where what you have in the reservoir, the IPR driven by the IPR, and the VOP, where it actually comes into equilibrium. And at that point is what you're going to get at the surface. So that is very, very most important thing here. And this is how the VOP curves looks like. And the IPR, typically this is how you see VOP curves. Then at the first pressure, there's going to be a sharp pressure drop down, then before rising and rising and rising till up there. So there are summary of those results here as populated by Prosper, then further information here. So can plot a lot of things. So what we just plotted is IPR curve and VLP curve, which is what we're interested in. We can see change in skin, total skin, completion skin, gravel path skin, IPR test point, as the case may be. So let's just limit it to that the sake of time. So we have our IPR. You can remember we have three curves now. Firstly, we generated an IPR curve showing our absolute open flow. Then secondly, we are generating IPR and VLP curve, identifying the amount of the amount of oil that can be delivered to the surface, which is somewhere here, and it's around 6,377. So that is very, very important. Then can click finish on that. Then another thing I want us to do is, okay, we've choose this gravel pack permeability. So Prosper will allow us to model like, okay, let's choose the best. So it will help us to have varieties of options. And how do we do this is through system sensitivity analysis. So we want to have like different kind of a scenario of our gravel pack so that we know that, okay, this is the best we are going to go with. And we'll go from there. I think that's the last thing I'll be doing here. No. Done. So now this is the page. If you can remember when I selected calculation, system IPR and VLP, there's an option for me to select three variables. So one of those variables I can just say I do a lot of things at the same time, but I'm going to stick with just okay, you can do reservoir pressure for system sensitivity analysis. You can do reservoir pressure, temperature to determine your optimal temperature, optimal pressure. These are all the things that Prosper will allow you to do. So, but I'm interested in gravel pack permeability, which is a use case. Let me look for it. You can't see it yet. Okay, so let's assume first let's just have like 5 cases. The first case is 15,000. The next case is 20,000. The next case is 25,000. Then you remember that I choose 30,000. So let's include it here. Who knows if that would be the optimum permeability. Let's have another one at that. So we're going to carry out system sensitivity based on these 5 different gravel pack permeability. So let's see what happens from here. So you continue. So still have these previous results, then we'll come to calculate again. Okay, so we've calculated for those cases. If you come here, you see that this result you are seeing is gravel pack permeability of 15,000. You can go, because we have 5 cases, change to 20,000, you see different results. Change to 25,000, you see different results, but I'm more interested in looking at the results from the graph. So let's plot it and see, choose system plot again. So why am I having nothing showing here? Okay. Oh, I don't know what this is all about. I'm supposed to have those 5K. So now you can see if you observe very well, our VLP remain and is 1. Because what we are dealing with is this VLP is just what is happening in the tubing in the well bore that's beneath the hole to the surface, so we only have 1. So, but what we are trying to optimize here is our reservoir, and it's true you do gravel pack to reservoir, not to alter anything on the. So if we are going to have different curves, maybe we'll started looking at the varieties of tubings, comparing tubings and all those things. That is not the analysis through tubing, but we are restricting this to the reservoir. So now the first one here, which is 0, is a gravel pack permeability of 15,000 millidasy. So which is our result here is not so good. What we'll be having deliver into our well bore is very to the surface rather is very low compared to when we have 4, which is having a higher flow rate, even better than what we have for the 30,000, which we choose earlier. So when you try to increase those permeability, though they have their own effects too. So you want to just minimize it so that you get your optimal operate. One of the effects is skin, causing of skin, as we noticed the other time. So skin around so damages around the wellbore. So, but we want to select in these 5 cases now. If you have to select the optimal, so I will definitely go for the 35,000, but we wouldn't want to go further and further to avoid damages into our reservoir. So near the wellbore. So that is all. It's this 5:30 already. I think so that's just the use case now. Like I said, Prosper has a lot of functionalities, which if you can, I think I have the documentation, you can look at the documentation and try out a lot of things yourself. Funny enough, this can be self-learned because I told you how I struggled to get it in the first place. So for you to even know that nobody is even there to teach me, so I have to self-learn, do a lot of things on my own. So let me just quickly show this, then we'll call it a wrap. So I have made mention of gas lift. So you still require all this information you've entered because that's if you want to do case O. If you want to do gravel packs, which you know is possible that you can still do gravel pack, at the end of the day, you still need artificial lift. So what you just do is come to system summary. Let me do that again. System summary. Then you come here to artificial lift. Then I said we have ESP, which is electrical submersible pump. We have hydraulic drive, all this jet pump, diluent injection, multi-phase, sucker rod pump. You can also model that using Prosper. Then you can do gas lift intermittent, but I will choose gas lift continuous. Then I will do done. So it will bring another interface here for you to enter gas lift data. So let's assume, yeah, I won't be going deep. Let me say gas lift gravity is 0.7. Model percent hydrogen sulfide, nothing like impurity. We leave it that way. Done. Then you come to design. You do gas lift. Then you choose new well. So it will bring, yeah, which you enter your data. After you enter your data, you see, put all this required data, maximum gas available, enter design rate, enter by user, calculated from mass production, all those things. Rate type liquid, design rates, you put it there, all those information. I don't have them now. Then you put current valve type, gas lift, is it Camco, is it Baker, is it valve, all those things. That will help you design your gas lift, and you can also visualize it the way we visualize the other one. So yeah, I think the time is fast spent. I think I will be stopping here.
Okay, thank you very much, Mr. Olaimi, for that insightful session. We'll move on to the question and answer segment to be handled by Precious. Over to you, Precious. Is Precious here? Okay, if Precious isn't here, please, if you have any questions, we can put it on the chat or signify by raising hands up. Thank you.
Please ask question. Does it mean that we don't, am I too fast? We don't understand, or you understand everything? At least, okay. Okay. I think I'm seeing something on the chat. All right. Can I go ahead and read this out, or you're going to read it?
Let me read it for you, sir.
Okay.
Number one, on realistic scale, how is the data you're entering obtained? Number two, the mentorship program I started with you while you were here with us in book last year started in full scale. How you see ready?
Okay. On the first one, being the realistic scale, how is the data you're entering obtained? Yeah, I think this is the most, like, this is the bone of contention. This is bone of contention around it, because even as at the point I want to write my projects, like I was praying that I should get data. See, realistically, getting this kind of data, people entrusting this kind of data to you, most especially in this industry, is going to be very, very, very difficult. So what people do is they are open sources data, well, all far by Volf. Yeah, I think Volf feed. Yeah, so you can get those data from the open source unlimited. And I think recently I'm checking IEA, International Energy, what is it called? So I'm seeing that they are making some data available. So I don't know if you can check IEA, maybe you can see something like that. The involved feed is another source, but realistically, for you to get this data from the producing or the active well is very, very difficult. So one way or the other, I was able to get the data from my project, but it's not something I'm expected to to be broadcasting. So that was it. Then on the mentorship program, maybe you can reach out to me personally so that we have a discussion around that.
Okay, thank you very much, sir. I don't think anyone has a question again, but if you do, please, you can just write it in the chat box down below. Another question, sir. Why?
Okay.
I think because of time, I think if we can you can just drop your contacts, your email address, if that is fine for you, and we can send over those questions, or people could have those have your contacts and they send over the questions to you through that, if that's fine for you, and then we try to move forward.
Okay.
All right, that's fine then. Let me just drop my email address.
Thank you so much.
Thank you, sir. Okay, so next off, let's just move to the photography and networking. Going to be handled by Angus Daniel.
Um, um,
If Daniel isn't here, can we just put on our cameras so that we can just take the picture and then move to the last thing? Can you please turn on our cameras? And the others, please put on their cameras.
So if they're not putting on, I think you can just carry and just take the picture of the ones that are here.
Yeah,
Okay.
you can just stop sharing so we capture everyone.
Okay.
Yeah.
Okay. I'm done with that, sir. Okay. Thank you
Thank
very
you.
much, sir.
All right. Thank you. What's next on the agenda?
Okay, well, since the person that was meant to give the closing remark isn't here, I'm just going to start by myself.
I am
The
here.
Okay. So, on
Okay.
behalf of SPE Warri Student
Emanuela,
Committee.
I am here. I'm here to
Okay.
take the closing remark.
Okay, you're here.
Yeah, exactly.
Okay. Thank
Sorry,
you. Go ahead.
yeah, okay, I want to use this opportunity to firstly thank everyone for showing up. It's something that is really, really pertinent. It's a topic that is really, really pertinent, especially for students and YPs. I would like to thank Samuel as well. He really took us through a whole lot of things, starting from the theory for us to understand what the background is, not just launching into the software without having some background knowledge, talking about the reservoir and the production systems. And it also took us into several aspects in the input data, matching your data with the PVT data, the modeling, interpretation of the results, and all that. All of these are very, very important and very, very useful. We can see all of the use. I could understand some of the students, maybe it could be a little bit kind of complex, but the goal of this technical presentation was just to have us understand what it looks like in real life. I mean, we do a lot of the calculations in classes, but at the end of the day, you have to show that you have the skills when for employability reasons. And this is where this software comes in, and this is something that is really important and pertinent. Thank you so much. This has been very wonderful, very enlightening, I would say. And I hope for some of the students and YPs that have been here, they've been able to have at least, they could see that they could self-learn or they could find this software. Perhaps they could contact you and all that and discuss how they can have it and try to practice as well and do something great. And yeah, thank you so much, everybody. Thank you, Samuel. Thank you, everyone, for showing up. Yeah, on to the next. Goodbye, everyone.
Thank you. Goodbye.
thank you. Goodbye all.